step only depends on the, let's
Yes,
say, the previous step to be at stage at just the next stage.
yes,
It's like n+1 can perform when n is just at 2.
exactly. Also, you can see some of the stage will be more heavily dependent on CPU. Some of them are heavily dependent on the I/O and the disk. So they are also divided into different stages to better utilize the CPU and I/O disk, those kind of things.
All right. Hi, I'm Shane Barratt. I'm a research partner at Hack VC, and I'm joined today by Wish, who is the CEO of Pharos Network. Wish, do you want to introduce yourself?
Yeah. Thank you, Shane. Nice to meet you. I'm Wish. I'm the CEO and the co-founder of Pharos.
Yeah, so you were telling me that you kind of had some history to Pharos. Do you want to go through that? How you guys got started, and where you are now?
Yeah, sure. So we starting from 2017. It's we are in the academia labs under the Alibaba Damo Academia, and then from 2017 we started this. We grow it from a lab to a research to a business group called Ant DT, and then we built the largest blockchain platform in Asia. It's called Ant Chain. So I think it's last year, 2025, we come out and started Pharos. So Pharos is a EVM compatible high performance layer one, which was based on the same tech stack that we built Ant-Chain. That time we successfully support over 1 billion users activities on this blockchain, and also numerous industries and user cases like ABS between banks and supply chain finance, etc. And also many of the user cases in the government. So, but it's a consortium blockchain, but we make it a public blockchain in Pharos, and it's all the tech stack are based on all those innovations and research outcomes what we build in the end. And so it's a completely new tech stack, starting from the consensus, the storage, execution, and all things are innovative, new research result by us. And but we make it a layer one, high performance layer one to reach 2 gigabytes per second. And so last year we saw Pharos, and then we quickly closed our seed round, and then we launched the testnet in May of this year. And recently, I think everything goes well, and we get a lot of attractions on the testnet, and we are envisioned to build this new layer one as an open finance layer to bridge the Web 2 and Web 3. And also we get the investment from many of these Web 2 fintech companies and public companies, including Ant and YF Capital and Sumitomo, etc. So basically, those Web 2 companies that are willing to enter the Web 3 through this open finance infrastructures.
Awesome. Yeah, so do you want to get into kind of the design of Pharos and the key components like consensus and achieving 2 gigagas per second, because it sounds reasonably impressive.
Yeah, so I think so. The blockchain is we have 3 layers actually. So the base layer is this consensus, and then we have this, we call it a pipeline, and it's the execution layer. And also, I think underneath of that, it's another, we call it a storage. And
So out of all these, pipeline seems like the one that I kind of haven't ever seen or seen
yeah,
often.
Yeah. So let me draw this and underline under the in parallel is we call it SPN. It's a more about heterogeneous hardware. So starting from the storage, yeah, let's starting from the consensus first. Okay, here. So our consensus is we call it asynchronous BFT algorithm, which allow so different from other BFT algorithm is that we allow multiple validators to propose the block simultaneously. So that we let me see, we call it async BFT. So basically, this allows multiple validators propose the block simultaneously, which could better utilize the network because originally no matter what kind of consensus, especially BFT consensus, they have lead proposers that could need to handle all the blocks. So it becomes the bottleneck. If it's a really high throughput, that node will become a bottleneck because the network is not a need a very high bandwidth for that node. And also, if that node crashes, it will make all whole the consensus crashes. So the
Yeah,
security
there's
is
no block for that second.
exactly. So what we do is we allow multiple validators to propose a block simultaneously. So each of them will utilize their network better. And also we know that the node need to be more decentralized in different area. They have different network conditions. So this asynchronous mechanism allow validator to adapt to their own network. If you are in a very, how to say, rare region with lower bandwidth, slower network, you can propose a block less frequently, but you are still able to propose a block. It's fair.
So how does that work? Like if you draw a bunch of validators and like multiple are proposing at once, how does the network decide which block becomes,
Yeah. So
the one?
they are proposing different transactions. They are not proposing the same transaction. There is a determinist algorithm that could randomly set the transaction to assign the transaction to different validator. You are responsible to propose that transaction, but it's in a deterministic
Mm.
way. But
So
this,
like out of 1,000 validators, if you publish a transaction, you set it up such that it can only be proposed by 50. Is that
yeah,
how it works at a high level?
it's high level is like this way, and you are
Sure.
assigned to some of the transaction you should propose. So different validator will
Yeah.
propose transaction, but it's a randomly but deterministically picked. But if your network is not good, you miss the transaction that should be proposed by you, and for some period of time you will be slashed or punished if you didn't propose that. But if you are
Okay,
just
so there's like at each slot, every transaction could only be potentially proposed by one validator. Is that
yes,
correct?
yes,
Based on how the meshing works, I guess you could call it meshing.
yeah,
Um,
yeah, similarly the way, yeah.
so, okay, interesting. Um, and so what are the other aspects of async BFT that are important for you guys?
Another one is that it's more, as I said, it's more adaptive to different network environment. It allows different validator with different network environment could also propose the blocks quite fairly, but more adaptively to better utilize the network. And also, if because there is no need proposer, so it's not a dependent on a single proposer. So the network is more robust because there is no single point failure.
And so when they propose a block, you're basically just saying it's kind of like a list of transactions. Um, Once you have the blocks from 20, let's say, proposers, how do you then merge them?
Oh, because they are each blocks each validator are assigned to different transactions. So
Yeah. Are they
so
merged randomly or in a
uh
particular
it,
deterministic order?
so each how to say each validator is proposing one block. So you propose first, and reach consensus, the block will be generated first.
Okay. But at any given time step, oh, it proposes one block, but there's a deterministic order amongst the blocks because they're all proposing them at the same time. So
So
like,
yeah, so
who
they are
goes first
proposing.
in the blockchain is what I'm saying. Who gets,
That is undeterministic. It depends on the network, on the yeah, on how they reach the consensus. I think
but I
this
guess
way.
like if you're a node listening to the network, how do you then determine you've heard all these blocks, you don't know what order they're in? How does that listener know eventually what order they should be in so that they can update their local state?
Uh, Actually, there is a memory pool just like Ethereum. So with all transaction goes to the memory pool, and the order of those transactions in the memory pool is undeterministic. It's not ordered. So the validator has the freedom to, in Ethereum, the validator has the freedom to pick what kind of transaction they want to propose. But in our consensus, those transactions are assigned by an algorithm to some kind of a specific validator to propose.
Okay. But I guess my question is simultaneously a bunch of validators are proposing transactions.
Yeah,
Those then have to be ordered.
no,
Like, okay, no.
yeah.
Like a blockchain is just a sequence of transactions, right? In
But
state at the end of each transaction. So how do you then take those transactions and order them?
so
Like
because
eventually they have to be ordered, right?
yeah, eventually it's ordered, but when you are proposing the block, you don't know the order. But when it reach the it being reach the consensus finality by all these validators, it's finalized. The order is determinist. But when you are
Okay.
proposing that, you don't know when this block will be the first or second.
So do you want to draw how that works, how the consensus works, how after all of the proposals they are merged?
Yeah,
Like, I
actually,
don't know, that seems kind of non-trivial and
yeah,
interesting.
yeah. Actually, I have a we have a slides on
Well,
this.
it'd be probably better if you just draw it.
Uh, okay, okay. Let me get this. So, so originally there are, for example, in the Ethereum, there as the block like this way. So this is a validator A, validator B, validator C. Each of them were responsible to propose a block in a sequence way. But on Pharos, it's like this is A, this is D, this is C. So they are all proposing the blocks simultaneously, but they have when they reach the consensus, they will choose. For example, I will choose how to mark the color. So this one, uh, this 1, 2, 3, 1, 2, 3, 1, 2, 3. So basically the consensus, when they saw all those blocks proposed by different validators, they will choose, for example, they will depends on the network. This is not ordered. They will choose the, for example, the one from A first, probably then from the one from the B, and
Yeah.
then from the probably then from the, how to say, let's go back to 2, and then go back to probably then the C's first block. So basically, for each of this block, the order is an undeterministic, but for the block proposed by one validator, it's deterministic. So
Yeah,
this,
that's ordered.
yeah, that's order. But if between those validators, the order is not determined when they are proposing the block. but they're finalized when the block reaches this consensus.
Okay, so there's communication amongst all the validators to basically decide, okay, I've heard yellow one, so we're gonna finalize this.
Mhm.
And then enough I've heard blue one, so we're gonna finalize this, and so on.
Yeah,
And only at the moment that all the validators come to agreement that yellow one should be a block, then it just gets committed and all those transactions execute in order.
yeah,
Is that a high level how at a high level how it works?
yeah, that's
But
correct.
your point is that the consensus communication amongst all the validators to agree to submit a block is not the bottleneck. It's just the single proposer, like upload speed or something you could say.
Yeah. For example, here I give an example. So why this red C, I think it's C, the red one is, for example, his network is probably much slower. So you can see that the A already have two blocks being agreed, reach the consensus, and they only have this first block being finalized. So
And it's not even slower. It's just they literally could have slow upload speed or they're just further away. Like let's say
yeah,
the entire network is probably in like Asia, but they're, in
yes,
Antarctica or something.
yeah, yeah,
So it's like
exactly.
long distance. So the block gets there probably after two is like ready to go. Do you have
Yeah.
a rough sense on the block time? Or I mean, there probably is a set block time, but
So the currently in our testnet, the block time is around 0.2 second to uh
oh, wow.
0.8
Yeah,
second.
pretty fast. Yeah.
Really fast because there are always some validators quite fast, right? So they can propose a block very fast. It's more adaptive, and if there are most of them have a large latency in the network, the block time will be uh, longer.
Yeah. Awesome. So that's consensus. I think that makes rough sense if you want to go back to your
Yeah.
uh, design overview up to the left.
Okay.
Yeah. So what makes sense to talk about next?
So next is I think it's a pipeline. So basically, the pipeline I think. So basically, the pipeline is the way that a node is handling the different transactions. So basically, it's more like a pipeline in the chip to handle the OP code or machine code
Hmm.
in the. So one transaction has different stages. We are also following the most basic algorithm from the block STM, but more optimized way. And so we divided the transaction into 5 stages. So from the consensus to the ordering to the execution, and then to the IO level, and then to the how to say to generating the execution level. So with different stages, so different transaction can be pipeline in this whole algorithm to be um, more parallelly executed, but with to better utilize the CPU cores of the node. For example, in our testnet or even in the mainnet, we want to have the validator have either 16 cores or 32 cores. So each of the core will handle different stages of this transactions to better utilize the CPU actually to make it more faster.
Yeah. Do you want to break that down a little bit or draw that
Yeah.
system?
Okay. Let me try to.
And then obviously, it's not just raw CPU execution. It's like, what does the memory look like? And how do you take advantage of caching and stuff like that to make the execution fast as well, right?
Yeah. So basically, let me check. For example, this is a block n. This is n+1, n+2, and each transactions we divided it into different stages. For example, this is how to say consensus. This is stage 1, and we have this scheduler. This is stage 2, and then we have this execution. Then we have this IO to do the merkleization. Then we have this let's say let's say this is consensus finalize the bulk. So the word is bad. And
You just try to finalize.
yeah, final. And then last one is called the write to the DB. So basically, we are dividing the transaction into 1, 4, 5, 6 stages, and when we are handling the first the block, it's like a pipeline. You can see.
Yeah, so each step only depends on the,
Yes.
let's say, the previous step to be at just the next stage.
Yes.
It's like n+1 can perform when n is just at 2.
Exactly. It's also you can see some of the stage will be more heavily dependent on CPU. Some of them are heavily dependent on the I/O and the disk. So they are also divided into different stages to better utilize the CPU and I/O disk, those kind of things.
But actually, now I'm kind of confused because don't you have to execute and write the DB before like n+1 can properly read the state?
Oh,
Or
so basically, I think modern design of this modular blockchain, they already, most of them I think already like decoupling the execution, consensus, and DB into different modules. So it's not dependent on each other.
okay. But if you have a transaction that changes the state of a particular thing that is then has to be read in block n+1.
Yeah, that's in the cache, right? So when you are executing for example, you're executing the block
Okay.
1, and they change some of the DB, but the cache already been modified. It's just didn't flush into the DB.
Mhm. But I guess if you look at this, the execution of block n happens before the execution of block n+1. It happens literally in the next step. So it's actually okay as long as n+1 has access to that resulting state information.
Yeah,
Okay. And they're all synchronized.
yeah.
Cool. And so are there any details that you want to give about any of these steps that are unique to Pharos?
Sorry.
Are there any details of these 6 steps that are particularly unique to Pharos, like maybe a unique DB design or
Yeah, I think
anything regarding execution or scheduling?
yeah, it's all connected together. So here we are in the pipeline, and also this is a more like a high level parallelization. It's on the transaction level, specifically for the execution level and the DB level. We have this parallel execution to better even like optimize or accelerate this stage, and also for the DB. And at the execution part, I think it's compared with others, is not that much highlight here. So it's basically we are also based on some of the open source project, like get some idea from the open source project, like the Rust version of the EVM and also the EVM1, those open source project. We are also borrowing some idea from that. But for the storage one, I want to highlight is that it's I think after you down the consensus pipeline execution, many of those layer one or blockchain has realized the DB is actually the bottleneck in all those things, because eventually all those data need to
Memory
be right.
access.
Yeah, need to be right into the disk, right? You use SSD, and you need a very high performant SSD to handle those kind of I/O, especially if we're using the most of the blockchain are using the Merkle tree structure, and also let me get this here. So basically, currently, most of the blockchain storage they use how to say a Merkle tree structure like this. And also, they are using a KVDB. So the KVDB is just also a KV structure and with different layer to indexing the data. So what happened here is that when you are retrieving or writing some data in the blockchain, you need to first traverse this Merkle tree, right? So it's need to traverse the tree first, and then after you get to this leaf node, it's actually a key in the KVDB. Mostly it's a RocksDB or LavaDB. You get the key in the database, and you use the key to traverse this different layer of hash-based KV database again. So basically, you need at least two times of to traverse this data. First on the Merkle tree in the memory probably, and then you need to traverse the DB again. So basically, it's a very long path, and it has a right amplification when, especially when this Merkle tree getting wider and wider or deeper and deeper, and also this RocksDB may also be harder to read and write. So it's become a bottleneck in the I/O level.
Yeah. So do you guys have a specific improvement to that?
Yeah, basically what we do is that probably we need to open a new page. So basically what we do is actually we design a whole completely new database, which is natively for the blockchain. What we do is that, so it's a whole database. So this is a new database. So we integrated this Merkle tree structure directly into the database. And the Merkle tree is a version-based Merkle tree. So what this what the benefit of this is, firstly, we use this version-based data Merkle tree structure, which is indexed by the block number. So each block number, you have a different Merkle tree, and within different version, for example, V1, V2, it's a delta encoded. It's not a duplicate of the whole tree. It's just store the difference part. So the data is also compressed. But because it's indexed by the block number, so you may remember that for the blockchain, mostly you will firstly say, I want to read the data in block ABCD, right? Block 1112. Then you find this version of block of the Merkle tree, then you get this data. So it's faster to retrieve the data, and the data is also compressed by this. And
It's important for the pipelining because you have to store the last six
Exactly.
at least and have them quickly accessible.
Exactly. And another benefit of that is because the whole thing is inside one database, which means we can do some low-level optimization in this. For the Merkle tree, the hash is like 256 bytes, but for the disk I/O, so the minimum we call it chunk is 4K byte. So all the data in the disk is divided by 4K data. So if we have all this Mercury in the DB, we can pack them into a 4K data. So which means you when you access the data, if originally is you only access 56 bytes, but in reality you read a 4K byte from the disk.
Yeah.
That's the nature. But if we are doing this, we can align different data into this 4K. So when you are, for example, you are traverse this path, you are reading all the data from the 4K byte. So it greatly improves the efficiency from the very low level optimization.
But I'm assuming in most cases that the most recent information of the Merkle tree is probably in memory, right?
Yeah.
But I guess you're saying it still has to be flushed to disk.
Yeah. So the
Okay.
cache is definitely another level of optimization. I think many of the blockchain are doing that. Even Ethereum is doing that very good. So you need to cache that into memory, but eventually you need to touch the code data in the disk, or you need to flush the data into the disk. That would touch this DB level. Yes.
Yeah, or like for example, someone makes a transaction that touches state that hasn't been touched in 100 blocks.
Yeah.
Probably not going to be in cache. So you're going to disk for that anyways. Your point is that when you read from disk, you're reading 4 kilobytes no matter what. So you might as well like pack it in such a way such that the 4 kilobytes that you read is like all the information that you need.
Exactly.
Like you don't need as too much more. You're trying to minimize IOPS on the disk.
Yeah. So basically, the cache is a good thing. For example, I know that Mega is the layer 2. They are doing the way to use a very big cache to store mostly part of the database. They need like one terabyte of memory, so they can store majority of the Mercury, so it can be retrieved really fast. But for layer 1, we don't want to require that all the validator have a super high performant hardware to do that, right?
Yeah. Okay, so that actually covers storage, right? And execution. I mean, they're all coupled, of course. So when you say EVM compatible, so yeah, like what is the actual structure of like all the addresses and the state and like is it EVM or
Yeah. So all this Mercury structure and also the transaction and also the execution engine were based on some kind of open source EVM execution engine. That's all even compatible. And also for the user or developer perspective, all the RPC method will make it even compatible. But there are also have to be some slightly difference. It can be fully even compatible. Most of it are in the gas level. So because we are a parallel execution, and so which means the order of this transaction are kind of undeterministic when you are sending the transaction. It's not like Ethereum. So when we are like how to say the order are undeterministic, the transactions gas probably will be different because the data is different and it's how to say
are you talking about the gas price or the
yeah
gas limit?
the gas that consumed actually by the transactions different because
So the gas limit.
yeah. So
Okay.
for example, when we are replaying all the transaction on Ethereum mainnet to our network, so we found this gas cannot be make it exactly identical to Ethereum because the transaction ordering probably be different because all the transaction are parallel execution. Some of the transaction may jump back or forth to a specific transaction.
Oh, so you're talking about gas price and ordering, right?
Yeah, ordering.
Correct?
Yeah.
Okay. Not that you're rewriting the rules for what opcodes cost what amount of gas. Although you
Yeah.
might want to because some types of transactions are more parallelizable, so maybe you should take less gas. I don't know. Did you guys change any of the gas opcode to gas
So
cost
for a
mappings?
for a specific OP code, the gas price is identical to Ethereum, but because of the ordering, also change the gas. They have a new, I forgot the exact ERC, introduced this gas variation. You can get some refund if you are like a
Mm,
war and things, right? So the audience may change that part.
okay. So mainly regarding the gas price, because like on your network, there's still some amount of priority by setting a high gas price because
Mm.
within the individual validator that your transaction in a particular block sequence is assigned to, they're going to order things in the order of a transact of you know the uh the gas price. One
Mhm.
question I had is what how do you determine which validator gets a particular transaction? Like what is the data that goes in to deterministically decide that?
So basically, we have an algorithm. So they are choosing the which transaction should be assigned to which validator based on this algorithm. It's kind of really uh, quite random. It's based on the hash of the last block and also the sender's address and
Okay,
the timestamp. But once that is deterministic, the transaction is quite deterministic to be assigned to some.
to be
Uh,
assigned, but
yeah,
you could game it to be assigned to a particular validator if you wanted to.
it's quite hard. It's quite hard. Theoretically it's possible, but it's quite hard.
Well, couldn't you just generate a bunch of addresses and choose the address that
Yeah, if you are
points to a
generating
particular?
enough addresses, it's possible you can get the transaction you want to propose. But again, this algorithm is rotating between different validators. So I would say theoretically it's possible, but in reality
Mm,
it's kind of hard. So that's why also the MEV opportunity on Pharos is theoretically it's possible, but it's kind of quite difficult to do.
yeah, but of course it'll be there. Like there will be opportunities, and people will try to, you know,
Yeah.
exploit that. Um, so what else are you interested in talking about?
Yeah, I think the last part is let me say, let me see. There is another one here. So we talk about the storage, consensus, pipeline execution, and the last part is the SPN. So you can see that I put SPN as parallel of all those different level because this one is like how to say it's another dimension of parallelization. I would say because this allows those different heterogeneous hardware. For example, um, for example, the TE or the GPU. So basically, this allows th- some specific validator to support the uh, other heterogeneous hardware for the GPU and the TE. So let me check how can I do that. Let me check. So normally the network, for example, they have
And what does SPN stand for? Is it Special
uh,
Processing Network?
yeah, special processing network, right? So basically, normally, for example, here are all the validators in our layer one, and we can choose few of these validators. For example, this is three. They have a TE hardware. So basically, there is a special SDKs for the validator clients. They can utilize this TE hardware. So at this case, this three um, so can form or kind of we call it a special process network. It's a similar to what kind of a subnet works.
Hmm.
So this is three, probably three is too small, by the way. We'll make it for iteration. Yeah. So basically, they will have this special process network or subnet, so they can have some special transaction. For example, if it's a TE, they can have a private transaction between
Hmm.
this subnet. So for example, if this API is running by, for example, a bank, so we do a lot of business when we're doing the consortium blockchain with banks. So what do they want is that even in a consortium blockchain, they want to all the transaction being the private transaction. because they want to send some transaction between their clients, the bank's client, within that system. So we build this. Basically, we can customize SPN for them. So they will have their own. They will run in this several validators by themselves, or they can invite their trusted partners to run this validator. They can form a subnet. Within that subnet, they can freely send the transactions, private transactions, or of their internal clients between them together. But the benefit is that it's really fast. All this SPN is managed by smart contract. Who can join this network? Who can have what kind of a requirement for their hardware? They need to have a TE. They have a special version of SDK that they can handle their own internal transactions. But the benefit, another benefit is here, it's still on the layer one. It's not another layer or another network. So the liquidity is still be the same. When they want to transfer, for example, they are doing stablecoin transfer within their bank accounts, different clients' bank account. But when they are transferring out to another external clients or external merchants or individuals, you can send this stablecoin outside of this SPA. So that become a normal transactions. And also the whole security of this SPA is still guaranteed by the whole network's validator, because their transaction, although it's private, but it's still reaching consensus by all those validators.
Yeah, the entire history is still like
Yeah,
every
yeah,
time a transaction happens on the SPN, it happens on the L1.
yeah, yeah, exactly.
Okay, but it has private information.
Private information it can be easily customized to those institutions, because
Not necessarily. It's just private. You also mentioned GPU and FPGA and other
yeah,
devices.
yeah, for GPU, it's another story. It's about if you are using some kind of the AI, you want to have a machine learning model running on the node, and you have others that want to utilize that model's capability. For example, you are using agent based on those model, or you want to uh, borrow their, how to say, buy their computation power to run some your own handle the how to say handle your
Inference,
inference.
basically.
You can pay them using any kind of a token, and you can use their computation power to do that. It's not a privacy cases, but a computation power cases.
Hmm. Interesting. And so you guys are in testnet, right?
Yeah,
Um, yeah, do you want to lay out kind of like the timeline of where you guys are and where you're going to be in the near future?
yeah. I think we just launched our new another new testnet, which has a major update on this consensus layer to incorporating the staking mechanism, and also a huge upgrade on the modular architecture of this network. So uh, we are really close to the mainnet right now from the tech wise, and we are planning to launch the mainnet early next year. So just a few months to go.
Yeah, and you mentioned with consensus, it's proof of stake, so you'll basically get slashed if you don't include a transaction after a while, or if you propose, an invalid block.
Yeah,
Pretty similar kind of to Ethereum, except with the additional fact that, if you are obviously ignoring a transaction for too long,
yeah,
you
exactly.
also get
So
penalized.
yeah, for the tokenomics, we don't make any too much innovations. We are quite following what Ethereum is doing for the proof of staking. So we want to make it more because the Ethereum's proof of staking is battle tested. We don't want to have too much innovation on that side, and we want to keep it as similar as possible. Yeah.
Yeah, yeah, awesome. Is there anything else technical that you kind of want to cover?
Yeah, I think yeah, mostly all these things. Yeah.
Yeah, awesome. So you want to give kind of just like a summary or a summary of what you're excited about in the future for Pharos, like where maybe even a grand vision or where you imagine things going, like something that could, maybe not actually be possible, but you would love to happen.
Yeah. So at the very beginning that we want this network to be, how to say, it's really the word mass adoption. So, but it's not, it's more like connecting the Web two or the the digital life of people to be onboarding on the Web three. So that's why we want to have this first this high performance metrics because when we are uh, when we are building the end chain, so we have some kind of a we built the largest NFT platform in China, and we have lots of campaigns during the Chinese New Year in on the Alipay apps. So this is a platform with over 1 billion users. So they will join the campaign during the Chinese New Year to claim NFTs. So that's really it's more like a either a payment or e-commerce scenario that have a very large volume of traffic on this blockchain. So at that time, we decided say we want to build layer one also have this performance because eventually when it goes to the daily life of users, they need this very high performance. Uh, and also we are envision that currently we're starting from the order bay because we're firstly onboarding those institutions and some of those assets from Web two and also the capital from Web two, so that the users can enjoy the benefit from the traditional finance also in the crypto world. So that's the first step. But after those, we have enough asset and the liquidity and the users. I think the next step is on the payment. So we want to do not the pay fine. We want to do the payment that it's what the people are using in their daily lives, like the e-wallet and some of the you can pay with crypto in a merchant. You can pay cross-border set the how to say the cross-border settlement infrastructure behind those e-wallet and this payment network. So we want to be an infrastructure that's supporting those kind of payment for the user's daily life. At that time, I think that's why we set the target of our TPS to be 50K TPS because we do some research on the current Visa or Master network. Their peak transaction per second is 90K TPS for those payment network. We want to be at least in the same level, like 50K TPS to handle this future traffic when there are billions of users are using the Pharos at their daily uh, infrastructure and financial infrastructure. So I think that's the innovation for us to build this.
Yeah, awesome. Thank you so much for joining.
Yeah, thank you.